So Tanya and Kevin and I have been mulling over this idea, and this presentation is kind of a brain teaser presentation. You'll see results. There's actually results. So what I want to, what we're I'm obsessed with is we worked in these very large landscapes, and it's complex modeling. We're talking about million-acre, and we have gazillions of models. And is there a way to simplify this, to have not every time we go out on the landscape, not do 30 or 25 state and transition models, each one with 50 boxes and all that? So is it possible to do that? And what is the method by which we can simplify our model? Basically what I would call clustering. So it's kind of a selective simplification. And is it possible to, is it worth, and I want an honest opinion at the end, is it worth pursuing or not? If you say no, then that's the end of it. But, well, I'm a little bit more stubborn than that. So imagine you have Wyoming sagebrush. So this is part of Great Basin National Park on the south and west side of it. And this is Wyoming sagebrush. Up here you have a community in Mountain sagebrush. Each one of these models in this case has 53 boxes approximately. And these are basically big sagebrushes, Artemisia tridentata. They're two subspecies, and why not do one model? And if you start doing that, you can simplify things when you think of all 20 or 30 models you have. Is there a common ecology to do this? Now, this is not foreign to the Landfire project, because that's actually what they did. Landfire, if you take the big sagebrush shrubland 1080 model, it includes semi-desert and Wyoming sagebrush. So they already do this, but they do it non-spatially, and that causes problems. So the problem is that there's been a push to, and I know Leonardo is familiar with this, there's been a push to have our models emulate as much as possible the NRCS ecological site description. And if you've opened a soil survey and you looked at the ecological sites, there's a lot of them, and if you were to model every ecological site in the landscape, you'd probably shoot yourself. So I'm trying to go in the other direction. I don't want to go towards greater complexity. I want to go away from it. Although I'm a geek and I love complexity and detail. For us, it's not unusual in a 500,000 acre landscape to have 25 to 30 ecological systems. It's not unusual at all. You know, we always have 2 different kind of aspen models. We have 10 sagebrush systems and all that. The problem is that you get a lot of models and you get a lot of parameter values. So the cost of remote sensing goes up with the number of thematic combinations and system and classes within system. And we know that we can cut costs by up to 30% remote sensing if we simplify enough. And for us and for the customers we work with, that is a big cost. The biggest cost in our projects is actually remote sensing. We do our own remote sensing for all of our projects. Also, we work with mule deer, sage grouse, Utah prairie dog, and other things like that, and golden eagle. We do have density models for them that we connect to the state transition models. But the models for habitat suitability for these wildlife people don't really care about the 25 systems. They care whether it's a shrub. It's like carbon. It doesn't matter if it's Jeffrey pine or if it's Douglas fir. It's standing carbon. And the animals kind of view the landscape the same way. They look at structure. Is it a shrub? Is it sagebrush? They just don't care. So there's surrogate variables like elevation that compensate for the lack of complexity in ecological systems. And the species often just don't care whether it's shad scale or spiny hopsage. They just don't care. So why go through all this complexity? Why do that? We do it because the managers want us to do it. But we have to convince them that maybe they could save money and not need to do that. So if you're going to start what we call, I'm going to get into the clustering soon. If you're going to this thing, there's one thing you immediately realize: you have to do it spatially. You cannot cluster models non-spatially. You have to preserve the ecological integrity of the variation within a cluster. And the only way to do that is to use spatial multipliers. I don't know how to, you can do it non-spatially, but it becomes meaningless at some point because you have all this uncertainty that you're fudging over everything basically if you do it aspatially. So you must identify all the ecological processes that are important that you know vary with some gradient or soil or something, and you have to force it. So if you take that mountain ridge that goes from Mount Sagebrush all the way down into Wyoming semi-desert, so we're talking somewhere from 14-inch precipitation zone all the way down to basically 7-inch precipitation zone. This is a spatial, this would be the value, for example, of a spatial multiplier. I mean, you would have values everywhere in your landscape, but your fire return interval is at its highest up here. And so this is a 50-year fire return interval. By the time you get down the hill here, you had 110, 120 year fire return interval. So basically, they're all big sagebrush. It's all big. There's actually other things in there, but just imagine it's all big sagebrush. It's all the same ecology, but the parameters change with elevation. But it's still, you can think of it as one model, but there's a spatial gradient that screws up everything. So, but to do this, you have to know your ecology, know what are the dominant ecological processes that may have a gradient or something varies in space. You're going to be limited on what you can cluster. You can't cluster everything to one model and then have 1 million rasters that make you do this and that. Well, you could probably do that, but I don't know that anyone would love you for that. So what you have to do is that you're going to have maybe a landscape of 25 and you're going to end up with 10 clusters. But 10 is way simpler than 25. So give you an example. This is, you really need to know, this is the part where you really need to know your ecology. So if you're calling, you actually have to go in the field and you have to visit the site. You just can't model this. You have to know your ecology. But I did just an example here where this is a landscape. This is what we model. So us three, this is a landscape, and I will find all of these ecological systems and more sometimes in a landscape, all of these. And here are the clusters, the name of the clusters. So all the big sagebrush can be put in one model. All the sub-xeric woodlands can be put in one model. And I just made this up like this, but it's consistent. All the basin wall rise, the grasslands, so the riparians, all the aspen, the high elevation conifer, limber, Engelmann spruce, and mixed conifer. What distinguishes these systems, sometimes it's all the same species, but the subspecies varies, but sometimes the structure of the model is the same. What varies is the gradient between them. It's not important if it's white fir. Our mixed conifers in Nevada is pure white fir on these north steep slopes, high elevation. It's totally unimportant whether it's white fir or limber bristlecone pine. What varies between them is that you go from a very harsh, dry condition to a deep soiled, north-facing slope. And that's what you have. So this is an example of how you'd simplify this. This is actually difficult to do, and when you start building the state transition model, this is where you start pulling your hair. This is actually, you have to justify this, and it's not that easy to do. So don't understand this model, but this is the big sagebrush model. This is for us our typical work. This is one ecological system. This happens to be either the Wyoming big sagebrush or the mountain sagebrush model on upland soil. They're both on upland soil. The reference condition is right here. You know, early successional, and this is with the tree phase and all that, but still recoverable to the reference. This is all reference classes. Everything else here is uncharacteristic classes. Either with cheatgrass, a seeding, depleted sagebrush where you lost your native grass underneath because it's been overgrazed or something like that. So what I've done is I've tried to find my most complex model, and I have to selectively, with my spatial gradients, my spatial multipliers, I will turn off some of these arrows. Wyoming sagebrush semi-desert, these two boxes do not exist in it. Only these three boxes and whatever is associated. In the mount sagebrush and the upland soils of Wyoming sagebrush, these two boxes are present. So my spatial gradient has to turn these boxes off. Everything that goes has to be turned off by the spatial gradient. And that's how you start with your complex model, and you let the spatial gradients simplify things. So you build one model. There's two ways then you can proceed. You may have a distinct question, and you're going to simplify classes. You're going to start lumping classes together because you don't need all this complexity in classes right off the bat. It depends on the question you're asking. And then you'll remove deterministic pathways. The only way you can actually turn off these classes I don't need in the semi-desert is if my deterministic pathways become probabilistic pathways. It's the only way to do it. The other approach is that you do the reverse. You remove the deterministic pathways, and then you eliminate the classes depending on your question. You may not need to eliminate classes. I prefer this approach because I like to keep the complexity of I'm very comfortable with 53 classes. It doesn't bother me at all. But this is the approach I prefer. But the reason for doing this part, removing deterministic pathways, is only for one reason. You have to have probabilistic pathways. You still have succession, but this you cannot control with a spatial raster. A spatial, you know, this transition spatial multiplier cannot be controlled, does not control the green arrow. It only controls the blue arrow. So deterministic has to become probabilistic in your model. And let's go with this. So this is part of that 50. So this is a screen capture of part of that 53 box model. And this is the reference pathway with native plant seedings and here cheatgrass crap and all that. So here are the green boxes. And here's the other model where I removed them all. And I converted to probabilistic transition. You'll notice here there was actually one that already didn't have a pathway. This one is a tree invasion. It's the establishment of ping and juniper in a shrubland at the early successional phase, when the little Christmas tree phase, we call it. This is already a probabilistic transition, this succession pathway. And the reason we did that is in our climate change models, and not just climate change, climate variability, we do it for climate variability, is that we want the dry and wet year condition, soil moisture, basically, the drought index, to modify the rate at which trees invade the landscape. We do the same thing with cheatgrass, but since the difference between these classes and these classes is tree presence, we use climate to modify whether you're going to have tree invasion in that year or not in a pixel. So this is the first thing you do, and if you do this for 53 boxes, it's kind of tedious. So these two guys would tell us, well, you should go to R coding and just get rid of them. That's fine. That's fine. So maybe you need R coding, but I did it manually, and it was a pain in the neck. Since I was told to provide for you who were in the class, the other class, we didn't do this, but in the intro class, you basically have from A to B, and here at age 19, it transitions from class early successional to mid-successional sagebrush, big sagebrush at age 19. You get rid of it here, it goes from A to A, and I create a succession pathway. And I like this for another reason, is that basically it starts at year 19, minimum age, but I actually spread out the transition. When you think about it, we do this for simplification. If you're a sagebrush plant, you're late year 18, I grow up, I'm 19, and all of us suddenly go to the other class. It doesn't work like that in nature. So this actually allows you also to spread it where there's a stochastic element to succession. This is the kind of Jim Merzenich version of the world. For those of you who know Jim Merzenich, kind of actually the father of VDDT type of thing, all his succession pathways were all probabilistic. He never used deterministic. And this was one of the reasons, because he wanted to be more real, the succession to be more like real data. So first step, you do this, and you'll say, well, this was boring, blah, blah, blah. And then you go to the next step is you reduce the classes. You do not need to do this. You may want to do this, and it depends on your question. You may have someone who pays you money to do sage grouse management, another one to do mule deer management, another one for fire management, weed management, and all that, and they have different questions. But what's important is that the simplification you do at the class level, this is your basically eliminated class because you don't want to deal with 53 classes, is because you just want to eliminate them, but you may not need to eliminate them. For example, for sage grouse, we know from the habitat suitability models of sage grouse that sage grouse view these two classes identically. They don't care whether there's a little bit of ping and juniper in central Nevada. It's not true in Idaho and other places, but in central Nevada, sage grouse, as far as they're concerned, this is one and only one class. These two classes are viewed very differently by sage grouse, and this class is non-habitat for sage grouse. But these two classes, they don't care. So the problem is if you do this for sage grouse, and 1 year later, the manager says, oh, now we want to do mule deer, and you've already simplified your model, and you have to go back and add those classes back, because it just happens that mule deer sees those differently, but they do not see those two differently. You see, you're a little bit screwed. So that's why I prefer keeping the classes and I deal with the complexity, but depends on your question and your patience and that stuff. So now we're getting into the spatial multipliers. Did Leonardo, you guys do this in the intro class? Yeah. Okay. Basically, you want to identify the strongest gradient in your models. So there's a lot of parameters we have in our models that do not vary spatially. Cheatgrass invasion rate is typically one. It's not high elevation. but wherever it's present, it happens more or less at the same rate. There's not a whole lot of elevation differences up to a certain level. So basically, all fire here, so this is the transition spatial multiply menu in advance, and all fire here, you'll put a raster there, and this raster is going to determine where on the landscape is the fire suppressed or magnified, or no, retained as is in the model or suppressed. And basically, you find your highest pixel and everything else is degraded. So at the highest elevation, I have a 50-year fire interval and I respect it. And as I go down in precipitation zone and lower elevation, I suppress my fire interval. So basically, 50-year fire interval is 0.02. 0.02 multiplied by 0.41 gives you the new probability per year of that fire in the semi-desert Wyoming big sagebrush. And if you want to see what it looks like, this is my dummy landscape that I made. Basically, imagine these two blobs are your entire landscape. And this is a precipitation gradient from more precipitation to less precipitation. And here you have a soil difference. For big sagebrush, from remote sensing, we determined that big sagebrush is here. This is the top of the mountain. I know this is a 50-year fire interval. And my spatial raster suddenly starts going downhill. I have contour lines here for precipitation. I took it from the prism data or something like that. And down here, I suppress the fire interval by a certain amount. So this is how I do the big sagebrush. It permits me to capture all the variation I need to capture. For dwarf sagebrush, which is low in black sagebrush has the higher fire interval. It's on the root restricting carbonate soil. So there's a calcite layer at 16 inches about in the soil. 5 minutes, I'm screwed. And so you do the rasters these way, but you need to cover your whole landscape. So I did these simulations. We took Great Basin landscape we did for the Barrick Gold project. I took 8,500 acres out of it, did these scenarios with action, no action, custodial, and I could compare between the class. So I'm going to go fast on this. We went out of our way to give you results and getting stuck. So, but this is actually what the landscape looks like. This is an old iron ore mine in that area. Basically, what I want to show is this is the unclustered version of low and black sagebrush. This is what, this is what you start with, and this is what I got. And what you'll notice if you look here, there's a separation here, and here you don't have it. And what I forgot to do, and this is an error I made because I was in a hurry, I didn't ask Tanya to provide me with a raster for grazing, horse grazing. So basically, if I didn't low black Wyoming, the elevation difference, these two systems are grazed differently by wild horses. They're not wild horses, they're feral horses in this case. And in this model, they view everything as the same. So I made an error in the model. It's an instructive error, actually. And what I get is that I didn't get the separation that I should have obtained. If I do a gradient for grazing, then they separate. So basically, this is a case where I didn't do my due diligence, and I paid the price for it. I made an error. Unclustered big sagebrush. So again, notice these difference here. And I go here, and then there's no separation. And it's entirely due to the grazing. I'm going fast now because I'm going to skip this. I'm going to skip that. And this is the fire behavior. And the big difference is that you have clustered, unclustered, no grazing, and no grazing. And the biggest difference here is in the grazing, as you see for fire behavior. There's less fire here. The reason is that there's a time since transition in the model. If grazed, the fire is suppressed. The horses really graze crazy. If they eat the cheatgrass, they suppress the fire interval for just 1 year in that pixel. And so this is why when clustered, I didn't do this thing, but here there is grazing, and it's selectively in mountain sagebrush actually repress the fire. And I'm going to skip this because there's also a moth problem. But you see the difference between the feral horse grazing. This is cattle grazing in the fall. This is and the big difference. And this difference is what explains it. I made an error. I found the error. I know why it is. It's instructive. So conclusion, I'm going to skip this. There are conceptual challenges here, and this is the important part. You can kick me in the butt if you want me to stop. But in order to do this, we have to rethink the natural range of variability and ecological departure. We actually have to make them spatially explicit. When you do this stuff, you can, the meaning of imagine you have a gradient of big sagebrush. The natural range of variability and the ecological departure you may measure means nothing. Because you're saying, I have trees in the NRV, I should have 5% of my landscape means, yeah, I should have trees. I know very well that you will never have trees in Wyoming semi-desert. It's impossible. It's physiologically impossible. So your NRV is incorrect, and you have to make the natural range of variability and ecological departure spatially explicit. We have to change how we think about departure and all that when we do this thing. Also, for you guys, what we have is that the transition rate changes. You can modify it with a raster, but when you do seedings, the failure rate decreases as you go in elevation. Your seedings are more successful with more precipitation, higher elevation. The raster has no effect on the proportions. This is something we cannot do currently with STSIM. Maybe it's done in R, I don't know, but it's impossible to do this currently. And if you do this, we have to address this problem. Otherwise, our seedings, we have no way of increasing the successor seeding with elevation. And I just want funding to do this. And here I actually propose formulas to do the spatially explicit ecological departure, one using the T statistics here for variability reasons, and also for the natural range of variability. So in consideration, I'm going to stop right here. Thank you.
Time for one very quick question. Hey, Louis, just one comment. That thing that you said that can't be done in STSIM.
It can be done in R.
No, it can be done in STSIM. You just have to name your transitions differently for whether it's successful or failure.
Okay, well, I want to talk to you because we couldn't figure that one out.